I'd like to talk a little bit about rates of change. And first thing I want to give you is this is actually a review from pre-calculus. You saw it last year. The average rate of change over an interval AB is going to be equal to f of b, that's the y value at the end of the interval, minus f of a, y value at the beginning, over b minus a. Keep in mind, by the way, you might notice, you might not notice, this is actually the slope of the line between the points at A and B. The next thing I would like to talk about is position function. By the way, that S is not meaning to pluralize the word function. Actually, in calculus, we oftentimes use the variable S to represent a position function. Another one that we use frequently is X. That one gets used in physics also. So if you see S of t or X of t, that's most likely going to represent a position function. So the position function is exactly what it sounds like. It gives the position of an object, and then it's going to be as a function of time. And usually we write it as either S of t or X of t are the two ways you often see it written. The next thing is the average velocity. So average velocity is the same thing that you might remember from physics. All it's going to be is the change in position over the change in time. And you'll most likely see that written as delta S over delta t. The last thing is our instantaneous velocity. So this is the one that we find the most often in this class. The instantaneous velocity is the velocity at one specific moment or instant in time. And this is found by finding the derivative of the position function. I'd also like to talk just a little bit about the acceleration. So to find the acceleration, you are going to do the derivative of your instantaneous velocity, which is also the second derivative of the position function. So let's go ahead and do an example. So when you're looking downward from the top of a 300-foot tower, your sunglasses fall off. Their height is given by the position function S of t equals negative 16 t squared plus 300, where S is measured in feet and t is measured in seconds. We're going to find the average velocity and we're going to find the instantaneous velocity. I just want to make a side note. You don't need to write this one down, but just in case you're wondering, in physics, you might remember we found the position or the distance by doing d equals 1/2 gt squared. Actually, g is 9.8 meters per second squared. In feet per second, however, it is equal to 32 feet per second squared. 1/2 of 32 is 16. That's where the 16 comes from. So if you notice that a lot of position functions have a 16 in them, that's why. So sorry, that was a side note, but I thought I would point that out in case you were wondering about that. For A, our average velocity, remember we're going to do that by finding the average rate of change. We find the change in position over the change in time, and you can actually do that by finding the average rate of change. So find the average rate of change of the position function. So we're going to do S of 2 minus S of 1 over 2 minus 1. So please use your calculator on these types of problems, by the way. Usually you'll get a calculator on this type of thing. You don't generally have to do big numbers by yourself, by hand. So S of 2 is 236. S of 1 is 284. That's going to be over 1. So we end up getting negative 48. And make sure that you get the correct units. If you want, as you're doing these, you can label them. So like the 236 is one of our S's. We know S is in feet. The 2 and the 1 those are the T's, those are in time. So we know those are in seconds. So this is going to be feet per second. So for part B, it asks you to find the instantaneous velocity after 1 second and the instantaneous velocity after 2 seconds. So remember that to find the instantaneous velocity, we take the derivative of the position function, which is just going to be s prime of t. That's actually going to be our velocity, which we usually write as v of t. So when we take our derivative, we get negative 32t. So after 1 second, we are going to find that just by doing v of 1. And our velocity is negative 32, and we're in feet per second. By the way, keep in mind that this is a negative number. The reason it's negative is because the velocity is going downward. After 2 seconds, we do v of 2, which gives us negative 64 feet per second. All right, the last thing I asked you to do is find the acceleration after 2 seconds. So to find the acceleration, that's a of t, you are going to do the derivative of the velocity, or you can think of that as the second derivative of the position function. So I just found the derivative of the position function, which was the velocity. Derivative of negative 32t is just going to be negative 32. And that's actually going to be in, not meters, feet per second squared. So every time you take a derivative with respect to t, by the way, you're going to be adding an extra time unit on the bottom of your fraction. I do want to point one thing out. If you're in physics, you might be really confused about this. Generally in physics, we say that if something is falling, the acceleration is positive, and if something is rising, it's negative. Different physics classes are going to have different conventions with that. For this one, based on the way the position function was written, they made it so that something going downward is negative. Just keep in mind that there are going to be differences between that. So if you take a physics class in college, it's likely that you might see either way of writing this. The other thing I want to mention with this acceleration is that you'll notice I didn't actually have to plug in the 2 seconds. The reason for that is because it is constant acceleration, which hopefully you remember based on what you know about the acceleration of gravity. The acceleration of gravity is always constant. So this one actually doesn't depend on your time. So we're going to do one more example. So you are diving off of a cliff, and the cliff is 32 feet above the water. So the position equation is right here. I want you to keep in mind that this equation is a negative parabola, which means it's an upside down parabola. It's not necessarily going to be going straight down, and actually it's the path of the jump is more like this. And then you have the water below here. So just keep that in mind as you're doing these. So the first question is, when do you hit the water? First of all, when you see the word when, that means you're looking for time. Hitting the water in this case is going to mean that the position, the s, is equal to 0. So you're just going to set your equation there equal to 0. And then solve for t. You can do this on your own if you want to pause and try it on your own. So when you solve this out, easiest way to do it is probably to factor out a negative 16. You get t squared minus t minus 2. And if you factor that out, you get t minus 2 times t plus 1. Your values of t are going to be equal to 2 and -1. Now, we're not going to go backwards in time, so the second answer isn't going to make sense. So we're just going to use the positive answer. So our answer for that is you hit the water after 2 seconds. Part B asks, what is your velocity of impact? So in order to do this problem, you actually needed part A, because otherwise we wouldn't know how long it took us to hit the water. So our impact is going to happen at time t equals 2. In order to find the velocity of impact, we need to find v of 2. To find v of 2, you first need to find the instantaneous velocity. So I'm going to go ahead and find v prime of t, which is the derivative of my position function. And actually, it's not v prime of t, it's going to be s prime of t. Sorry about that. And that's going to give me my v of t. So my derivative is going to be -32t plus 16. Once I have that, I then can find my v2, and that's going to be -32 times 2 plus 16, and that gives me -48 feet per second. Keep in mind it's negative once again because it's going downward. So part C asks me what was my initial velocity. So my initial velocity is when t equals 0. So I'm actually finding my v0. So my v0 is going to be found using the vt equation. You don't actually have to really do any calculus at all for this one. You're just doing algebra, plugging in a point. So we're going to substitute in 0 for t, and we end up getting that our starting velocity was 16, and remember it's in feet per second. For part D, I asked you, when do you stop moving upward and start your descent? So basically it's asking you for the time that is right here on the picture. So there's a few ways that you can think about this. The first thing that I want you to remember is that if you have a trajectory of something that's moving up in the air, the trajectory, by the way, is the path. The very top point always has a velocity of 0. Now, I'm going to tell you the calculus reason for that. So if you're in physics right now, you maybe will understand this a little bit better. So the calculus related reason for that is that at this point, if I were to draw a tangent line, it would look like that, and it would have a slope of 0, which means that my position function has a derivative of 0 at that point. So the velocity at that point, which is the derivative of the position function, is equal to 0. So in case you were ever wondering about the top of a curve having a velocity of 0, that's the mathematical reason why. So basically we want to look for, it asks me when, so we're looking for time, and we want to know what the time is when our velocity is equal to 0. So I'm just going to use the equation I found in part B. I get 0 equals -32t plus 16. In this case, we don't want a negative answer because we aren't going to be going backwards in time. If you get a negative answer, you might have made a mistake in there. So if you solve this out, you hopefully should get that t is equal to 1/2 or 0.5 seconds. I'd just like to give you a few more things that you should probably put in your notes. The first thing I want you to know is that speed and velocity are not the same thing. You might remember this from physics class. So speed is what we call a scalar quantity. Velocity is a vector quantity. Speed will always be positive. So what you're going to do is you're always going to take the absolute value of the velocity function. Velocity can also be negative. So if the velocity is negative, then that's a sign that something is moving down or left, so it's going to tell you the direction. That's really important. And the other thing is, you're on the EP exam, they love these particle motion problems. It says particle at the bottom, but right here, it could be pretty much anything. So if velocity and acceleration have the same sign, that means that something is speeding up. What that means is that they're going in the same direction. If they have opposite signs, that means it's slowing down. For example, if they have an opposite signs, if the particle is moving to the right and the velocity is to the right, but the acceleration is to the left, an acceleration in the opposite direction actually means deceleration. So you probably just want to put these in your notes. We'll do some practice problems on these at some point.